Alright guys, for today's bell ringer, it says evaluate the expression 16 divided by 8 times 3 squared. So order of operations says that we are going to do 3 squared first. So what I'm going to do is I'm going to have 16 divided by 8 times 9, and then we can just go from left to right. 16 divided by 8 is 2, and 2 times 9 is 18. For the second question, it says evaluate 4x squared for x equals negative 3. And so if I plug in negative 3 for x, and the order of operations, 4 times negative 3 is negative 12, and then negative 12 squared is positive 144. For today's lesson, we're going to be looking at multiplying matrices. So this is lesson 2.3, multiplying matrices. So how can matrices be used in sports statistics? So it says professional football teams track many statistics throughout the season to help evaluate their performance. The table shows the scoring summary of the Oakland Raiders for the 2000 season. The team's record can be summarized in the record matrix R. Just keep in mind, why do we use matrices? To organize data. The values for each type of score can be organized in the point values matrix, or P. So what I notice here is that it says Oakland Raiders regular season scoring, and it says that there were 58 touchdowns, 56 extra points, 23 field goals, 1 2-point conversions, and 2 safeties. So we organized that information in a matrix right here, matrix R. And it looks like the dimensions of this matrix are 5 rows, 1 column. So this is a 5 by 1 matrix. Now, we know from sports that point values, you get 6 points for every touchdown, 1 point for every extra point, 3 for a field goal, 2 points for a conversion, and 2 for safety. So how would you actually determine the team's total point values for the season? Well, we'd simply multiply 58 touchdowns times 6, then we would add 56 extra points times 1, then 23 times 3, plus 1 times 2, plus 2 times 2. And so we'd add up all those values, and that would give us one number. So we can use matrix multiplication to find the total points scored. But how do you multiply two matrices? Well, you can multiply two matrices if and only if the number of columns in the first matrix is equal to the number of rows in the second matrix. When you multiply two matrices, A, that has dimensions m by n, and matrix B, that has dimensions n by r, the resulting matrix AB is an m by r matrix. So, let me show you an example. Let's say that you have matrix A, and matrix A is a 2 by 3. But then you also have matrix B, and matrix B is a 3 by 4. When you multiply these two matrices together, you have to make sure that the number of columns in A is equal to the number of rows in B. The two inner dimensions must equal. If they do equal, then that means you can multiply them together, and your new matrix, your product matrix, is going to be the outer dimensions 2 by 4. So that means when you multiply those two matrices together, you'll get a 2 by 4 matrix. So that's the rule for multiplying. So for this example, it says determine whether each matrix product is defined. If so, state the dimensions of the product. So what if you had matrix A, which is a 2 by 5 matrix, with matrix B, which is a 5 by 4? Again, make sure the two inner numbers match. If they do, your product is going to be the outer numbers. So in other words, the product of AB would be dimensions 2 by 4. Alright, for part B, matrix A is a 1 by 3, matrix B is a 4 by 3. The problem though, these are not the same, So we cannot multiply those two matrices together. So AB is not defined. So just remember, you can't always multiply matrices. But when you can multiply them, here's your rule for multiplying them. The product of two matrices is found by multiplying columns and rows. The entry in the first row and first column of AB is found by multiplying corresponding elements in the first row of A and the first column of B and an A. So for example, if you have a 2 by 2 matrix with A, B, A, and B, and a second 2 by 2 matrix with X, Y, X, Y, the way you multiply it is you multiply row times column. So you multiply the first row times the first column and add those two values together. So A1 times X1 plus B1 times X2. And so that gives you your first element in your new matrix. And so then you keep the process. You did the first row times the first column in yellow, so now do the first row and the second column. So A1 times Y1 plus B1 times Y2. And then you're through with the first column. First row. Now let's multiply the second row times the first column. So that'll be A2 times X1 plus B2 times X2. And then finally, you have to do the second row times the second column. So the A2 times Y1 plus B2 times Y2. And when you do those calculations, you'll get your new product matrix. So let's take a look at an example. So let's take a look at example 2. We want to find R times S. Well, the first thing I need to know is, can I even find RS? Is it defined? Well, the dimensions of R is a 2 by 2 matrix. The dimensions of S is a 2 by 2 matrix. You notice the two inner numbers are the same, so I can multiply them, and the two outer numbers are going to give us the dimensions of RS. So RS is going to be a 2 by 2 matrix. So the question now is, how do I get the elements that go in this 2 by 2 matrix? Well, the way we're going to do that is row times column. So let's start in green. So in green, row times column, it's going to be 2 times 3 plus -1 times 5. So I multiplied the row in the first matrix times the column in the second matrix. And so I'm going to get 2 times 3 is 6 plus -1 times 5. So that's going to give me 6 minus 5, so that's going to give me 1. Alright, and so now we can move to the second column. So I'm going to change to blue. So still the first row, but now the second column. And so I'm going to now multiply 2 times -9 plus -1 times 7. So 2 times -9 plus -1 times 7. So that should give me -18 minus 7. It's going to be -25. And so then that takes care of our first row in our new matrix. And so now we can move past the first row. We'll change to pink. So now we're in the second row, but back in the first column. So that would mean I'd have to multiply 3 times 3 plus 4 times 5. So that would give me 9 plus 20, and that would be 29. Alright, and then finally, still in the second row, but now in the second column. So what will that give me to multiply? That means I'm going to multiply 3 times -9 plus 4 times 7. So 3 times -9 is -27. 4 times 7 is 28, so negative 27 plus 28 is 1. And there would be my new matrix. My new matrix would be a 2 by 2 matrix with the elements 1, negative 25, 29, and 1 inside of it. Alright, example 3 says multiply matrices with different dimensions. Alright, in a 14-track meet, 5 points were awarded for each first place finish, 3 points for each second, and 1 point for each third. Find the total number of points for each school. Which school won the meet? Well, I noticed that there's 4 schools here, Jefferson, London, Springfield, and Madison, and it tells you first place, second place, and third place, how many people got those. So it looks like I definitely have a 1, 2, 3, 4 rows, 3 columns. Looks like I definitely have a 4 by 3 matrix. So what I have here is a 4 by 3 matrix with 8, 4, 5, 6, 3, 7, 5, 7, 3, and 7, 5, and 4. Now keep in mind, to multiply matrices, I have to make sure that whatever matrix I multiply by, you see how this has 3 columns, then that better mean it has 3 rows. And so what I have here is that it's 5 points for each first place, 3 points for each second, and 1 point for each third. So I need to make sure that I make a 3 by 1 matrix. That means 3 rows and 1 column. So that way I can multiply. So 5, 3, and 1. And see, now that I can multiply those two matrices together. My resulting matrix is going to be a 4 by 1 matrix. And the way we're going to do that, again, is row times column. So 8 times 5 plus 4 times 3 plus 5 times 1. So I'm going to have 8 times 5 is 40, plus 4 times 3 is 12, plus 5 times 1 is 5. So that would give me 40 plus 12, 52, plus 5, that would give me 57 for Jefferson. So that's how many points Jefferson was awarded. Alright, so now we can move down to the second row and multiply it by that column. So what would that be? That would be 6 times 5, so that's 30, plus 3 times 3, that's 9, plus 7 times 1, that's 7. So that would be 30 plus 9, 39, plus 7, so 46. So that means London was awarded 46 points. Alright, let's move on to the next one. So row 3, row 3 times that column again. And so what will that be this time? Well, that would be 5 times 5, which is 25, plus 7 times 3, which is 21, plus 3 times 1, which is 3. So 25 plus 21 would be 46. 46 plus 3 would be 49. So 49 points awarded to Springfield. And then finally, the last row times that column again. And so in this case, it will be 7 times 5 is 35, plus 5 times 3 is 15, plus 4 times 1 is 4. So 35 plus 15 is 50, and 50 plus 4 is 54. And so 54 points were awarded to Madison. But again, that's an example of how you multiply matrices. Alright, example 4. It wants to determine whether or not the commutative property holds with matrices. So if you notice for part A, it wants you to multiply P times Q, and then for part B, it wants you to multiply Q times P. So remember, the commutative property works in arithmetic, because you know that 2 times 3, which is 6, is the same thing as 3 times 2, which is 6. But the question is that property true with matrices? That's the question. So we have matrix P, which has dimensions of a 3 by 2, and we have matrix Q, which has dimensions of a 2 by 3. So for part A, it wants to know P times Q. So P, again, is a 3 by 2 matrix. Q is a 2 by 3. So we can multiply them, but notice we're going to get a 3 by 3 matrix. So I'm going to have a 3 by 3 matrix for PQ. But look at QP. QP, Q would be the first matrix, which is a 2 by 3. P is the second matrix, which is a 3 by 2. I also can multiply these together, but instead of getting a 3 by 3 matrix this time, I only get a 2 by 2 matrix. So clearly, these two matrices are not the same. So the commutative property does not hold up with matrices. You'll actually get different answers by doing that. But we're going to do this, we're going to work it out. So to do PQ, remember we're going to do row times column. And so what I'm going to get, if I multiply this, so I'm just going to PQ, let's put it, I'm just going to go ahead and just do a blank sheet and start over, that way I don't run out of room. Alright, so for PQ, I would do row, I'm going to do row times column, so row times column. And so that would give me 8 times 9 plus negative 7 times 6. So 8 times 9 is 72, 7 times 6 is 42, so negative 42, so that would give me 30. So, and then I'm just going to erase this right now because I'm not doing that one. So that means this element's going to be 30. And so now I can move, still in the first row, so still in the first row, but now in the second column. So that's going to give me 8 times negative 3, so that's negative 24, plus negative 7 times negative 1, that's 7. So negative 24 plus 7 is negative 17. And so now I can move to, still with the first row, but now the last column. And so that's going to be 8 times 2, which is 16, plus negative 7 times negative 5, so that's 35. And then 16 plus 35 is 51. Alright, and so now we're done with the first row, so now we can skip down to the second row, but now the first column. So I'm going to have negative 2 times 9, so that's negative 18, plus 4 times 6, so that's 24, then negative 18 plus 24 is 6. And so now we can move to the second column. Still the second row, but now the second column. And so that's going to be negative 2 times negative 3, so 6, plus 4 times negative 1, so negative 4, and then 6 minus 4 is 2. Right. And now we're still in the second column, second row, but now in the third column. So that's going to be negative 2 times 2 is negative 4. And then 4, let me make sure that's not a negative, well, I didn't put too much on there, that's just a 4. Okay, and so then 4 times negative 5 is negative 20, and so negative 4 minus 20 is negative 24. And now we're done with the second row. And so now we can move down to the third row, first column. And so that's going to give me 0 times 9 is 0, plus 3 times 6 is 18, so 0 plus 18 is 18. And now we're going to go to the last row, the second column. 0 times negative 3 is 0, 3 times negative 1 is negative 3, 0 minus 3 is negative 3. And now the last row and the third column. So 0 times 2 is 0, and then 3 times negative 5 is negative 15, 0 minus 15 is negative 15. And so there would be that 3 by 3 matrix for PQ. Now, as we already talked about, QP would not be the same matrix, because QP would actually be a 2 by 2 matrix. So QP would be where you first put the Q matrix, 9, negative 3, 2, 6, negative 1, negative 5. And the P matrix, 8, negative 7, negative 2, 4, 0, and 3. And so what we're going to do here now is, again, rows times columns. So I'm going to just highlight it. So row times column. So that's going to be 9 times 8 is 72. Negative 3 times negative 2 is positive 6. And then 2 times 0 is 0. So 72 plus 6 is 78 plus 0, so that's going to be 78. Now still with the first row, but now with the second column. 9 times negative 7 is negative 63. Negative 3 times 4 is negative 12. 2 times 3 is positive 6. So that would be negative 75 plus 6. That would be negative 69, I do believe. Alright, and then we can move on to the next one. So the second row, first column. So 6 times 8 is 48. Negative 1 times negative 2 is 2. And then negative 5 times 0 is 0. So 48 plus 2 plus 0 is 50. And then that leaves us with the second row and the second column. So 6 times negative 7 is negative 42. Negative 1 times 4 is negative 4. And negative 5 times 3 is negative 15. So negative 42 minus 4 is negative 46. Minus 15 would be negative 61. And so there would be the matrix QP, which is not equal to the matrix PQ. Alright, and so now let's look at if the distributed property still holds. And so you remember the distributed property is how we multiply and distribute by a scalar. And so what you're going to find is that the distributed property actually does hold, even though the commutative property does not. So for part A, it wants us to first add matrices B plus C together and then multiply that by A. Whereas in part B, it wants you to multiply matrix A and B together first, then multiply matrices A and C together, and then add those two together at the end. So let's give that a try. Alright, so let's go right here, and let's cross out this one first. And so let's start off. Matrix A is 3, 2, negative 1, and 4. And then matrix B is negative 2, 5, 6, and 7. And then matrix C is 1, 1, negative 5, and 3. Alright, so let's start by first adding the two matrices together and then inside the parentheses. So negative 2 plus 1 is negative 1. 5 plus 1 is 6. 6 plus negative 5 is 1. And 7 plus 3 is 10. And now I want to multiply that by matrix A. And I notice both of these are 2 by 2 matrices, so I can multiply them. And so that's going to give me a 2 by 2 matrix. So let's do row times column. So 3 times 1 is negative 3. So let me put that down here. So I'm doing row times column. So 3 times 1 is negative 3, plus 2 times 1 is 2. Negative 3 plus 2 is negative 1. And now let's do row times second column. So 3 times 6 is 18. 2 times 10 is 20. So that's going to give me 18 plus 20, 38. Alright, now we can move on to the second row. Back to the first column. Negative 1 times negative 1 is 1. 4 times 1 is 4. 1 plus 4 is 5. And then now the second row, second column, negative 1 times 6 is negative 6. 4 times 10 is 40. And then add that, that gives me 34. And so there would be part A. And what I want you to notice is we should get the exact same answer for part B. So now let's do part B. Alright, for part B, it wants us not to add the matrices together first, but actually multiply matrix A times matrix B, and then multiply matrix A times matrix C, and then add those two together. So let's start off by multiplying each one. So let's start over here on the left. So row times column. 3 times negative 2 is negative 6. 2 times 6 is 12. Negative 6 plus 12 is 6. And now same row, different column. 3 times 5 is 15. 2 times 7 is 14. And 15 plus 14 is 29. Now the second row, second column, so negative 1 times negative 2 is 2, and 4 times 6 is 24. 24 plus 2 is 26. And then the second row, second column, negative 1 times 5 is negative 5, 4 times 7 is 28, and 28 minus 5 is 23. So there's the first matrix. Alright, now let's move on to the second one. So 3 times 2, first row, first column, so 3 times 1 is 3, 2 times negative 5 is negative 10, and 3 minus 10 is negative 7. And so now, first row, second column, 3 times 1 is 3, 2 times 3 is 6, 3 plus 6 is 9. Alright, and then now we can go to the second row, first column. So negative 1 times 1 is negative 1. Negative 4 times negative 5 is negative 20, and so negative 1 and negative 20 is negative 21. And then second row, second column. So negative 1 times 1 is negative 1, and 4 times 3 is 12, so that gives me 11. And then we can add these two matrices together. So 6 plus negative 7 is negative 1, 29 plus 9 is 38, 26 minus 21 is 5, and 23 plus 11 is 34. And then just to compare it, negative 1, 38, 5, and 34, negative 1, 38, 5, and 34. And so sure enough, both of those matrices are equal to each other. Alright, so the last part of this is looking at some practice questions. So if you would, you could pause the video, give them a try, and then when you're ready to go over them, just hit play. So for number 1, it says, give an example of two matrices whose product is a 3 by 2 matrix. Well, clearly you can come up with any set of matrices that will work as long as whatever matrix A is, its columns has to equal the rows in matrix B. So like you could have a 3 by 5 matrix, and B could be a 5 by 2. As long as these two inner numbers match, then your product is going to be the dimensions of the outside numbers. So there's a 3. So basically what's circled can be any number you want, and then they have to match, and then the two outer numbers have to be 3 and 2. Alright, 2. Determine whether the following statement is always, sometimes, never true. For any matrix A, which is Mn, for m not equal to n, A squared is defined. Well, that's not true, because that would be A times A, and so you would have an m by n matrix and multiply it by an m by n matrix. Notice that that's m and n, they're not the same number. So that would be a never, especially if they're not equal to each other. Alright, so explain in most cases why A plus B times C is not CA plus CB. Well, because of the distributive property. So we know that if we distribute this C, notice that the A is the letter that comes first, so this would technically be AC plus BC. And if you remember, we said the commutative property does not work for matrices. So you see how it says AC? That's not the same thing as CA. So that's why that would not be in most cases true. Now what would be true is if the C was in the front of the distributive property, like in front of the parentheses. If that was the case, then yes, you could distribute your matrix and get CA plus CB, and that would be true. Alright, for 4 and 5, it says determine whether each matrix product is defined. Well, for number 4, those two inner numbers match, so that means they do, and your product is going to simply be a 3 by 2 matrix. The problem with number 5 is the two inner numbers do not match, so that product would not be defined. Alright, looks like 6 through 9, it wants you to actually work some out. So for number 6, it looks like this is a 1 by 2 matrix, and this is a 2, so yes, that can be multiplied. So let's do row times column, so it'll be 3 times 3 is 9, negative 5 times negative is 10, so 9 plus 10, so that'll be 19. So that takes care of that. And then the row times the second column. So 3 times 5 is 15, plus 0, so 15. And so that will be your answer for that one. Alright, for number 7, looks like this is a 2 by 1 times a 1 by 3, so you can multiply. Row times column, remember, so the only row is 5, so it's going to be 5 times 3 is 15, and then 5 times negative 1 is negative 5, and then 5 times 4 is 20, and then 8 times 3 is 24, and then 8 times negative 1 is negative 8, and then 8 times 4 is 32. So there would be our matrix for 7. Alright, for 8, looks like I can multiply these together also. It's a 2 by 3 matrix. Ooh, no it's not. It's a 2 by 3 matrix, and this is a 2 by 2 matrix, so I cannot actually multiply those. So, ooh, good save. Number 9 is a 2 by 2 matrix multiplied by a 2 by 1, so I can multiply those together and I'll get a 2 by 1 matrix here. So let's work it out. So let's do row times column, so 4 times 7 is 28, negative 1 times 4 is negative 4, so that'll be 24, and then row times column, so 3 times 7 is 21, plus 5 times 4 is 20, so that'll be 41. Okay? Alright, number 10, it says use A, B, and C to determine whether ABC equals ABC is true for the given matrices. So it looks like it wants to determine if the associative property is true. So does it matter if I multiply B and C together first, or do I multiply A and B together first? Do I get the same answer? So let's look at that. So matrix A is 2, negative 1, 3, and 5. Matrix B is negative 4, 1, 8, and 0. Matrix C is 3, 2, negative 1, and 2. Alright, so let's multiply the two matrices inside the parentheses first. So row times column. So row times column. So negative 4 times 3 is negative 12, minus 1, so it'll be negative 13. Now row times column, so that'll be negative 8, plus 2, so negative 6. Now second row, first column, 8 times 3 is 24, 0 times negative 1 is 0. Alright, and then second row, second column, 8 times 2 is 16. Alright, so that's that one. And so now let's multiply it by this other matrix. And of course the numbers are getting bigger, so let me put it below here and get my calculator out. So 2 times negative 13 is negative 26, minus 24 is negative 50, 2 times negative 6 is negative 12, negative 1 times 16 is negative 16, so that'll be negative 28, 3 times negative 13 is negative 39, and then 5 times 24, then that'll give me 81, and 3 times negative 6 is negative 18, 5 times 16, so that gives me 62. So there's that half. Well, let's see what happens this time if you actually multiply matrices A and B first, and then multiply by matrix C. Alright, and so let's see. If I do that, 2 times negative 4 is negative 8, negative 8 so negative 16, 2 times 1 is 2, 3 times negative 4 is negative 12, and then 8 times 5 is 40, and then 3 times 1 is 3, and 5 times 0 is 0. Alright, and so now let's multiply by that other matrix, and let's see what we get. They should match up. Alright, negative 16 times 3 is negative 48, 2 times negative 1 is negative 2, and that does give me negative 50. Negative 16 times 2 is negative 32, 2 times 2 is 4, negative 32 plus 4 is negative 28, so that checks out. 28 times 3 is 84, minus 3 is 81, that checks out. And then 28 times 2 is 56, plus 6 is 62, so sure enough, they check out. So the associative property does hold for matrices. Alright, I think, well, there's 2 more. Alright, and so for this one it says, write a matrix for the registration fees and a matrix for the number of players. Registration fees and for the number of players. Okay, well, the number of players is this matrix right here. So that would be 350, 280, 350, 280, 320, 165, 180, and 120. And notice that that's a 3 by 2 matrix. So if I want to multiply by anything, it's got to be a 2 by something matrix. Alright, so then it says for the registration fees, it says the West Fall Youth Baseball and Softball League charges the following registration fees. So it looks like 45, 55, and 65. Well, I can't make that into a 2 by 1, so it looks like I'm going to need to, because that's just going to be a 1 by 3 matrix, right? Because it's just going to be $45, $55, and $65. So that's a 3 by 1 matrix. So yeah, what I'm going to go back and do now is I'm going to add up baseball plus softball, because that will be the total number of players anyway. Alright, so let's just get a new sheet and let's do that. So 350 plus 280, so 350 plus 280 is 630. So that's the total players for ages 7 to 8. So then 320 plus 165 is 485. And then 180 plus 120 is 300. So that's for the players, and that's a 3 by 1 matrix. So I need to multiply that by a 1 by 3 matrix. And that 1 by 3 matrix is going to be 45, 55, and 65. And by doing so, I'm going to get a 3 by 3 matrix. Right, this is a 3 by 1, and this is a 1 by 3. So I'm going to get a 3 by 3 matrix here. Or, better than that, what I'm going to do is I'm going to flip them around, because when I multiply this, this is just going to give me, it's not going to add them up for me like I want to. So instead, I'm just going to flip it around one more time. And so instead, I'm going to put the registration fees first, so 45, 55, and 65. And that's a 1 by 3 matrix. And then, let me go back and add up those sums again. It was 350 plus 280, so that's 630. And then 320 plus 165, so that's 485. and then 180 plus 120, so that's 300. And so this is a 3 by 1 matrix. I still can multiply them together, but I'm going to end up with only a 1 by 1. And see, that's going to give the total amount of money the league received for all registration is that one number, and that's what I want. So 45 times 630 plus 55 times 485 plus 65 times 300. So they collected $74,525 in registration fees for all of those team members. Alright, last example. It says find the values of A, B, and C, and D to make the statement true. If the matrix ABCD is multiplied by any other matrix containing 2 columns, what do you think the result would be? Well, it would obviously change. Oh, well, it looks like it's asking what do you multiply a matrix by to get itself? Okay, well, it is a nice little challenge problem. The actual answer is 1, 0, 0, 1. And we call this the identity matrix. And see, what happens is when you multiply a matrix by the identity matrix, you end up getting the original matrix back. Let me show you. Row times column, 3 times 1 is 3, 5 times 0 is 0, so you just get 3. Row times column, 3 times 0 is 0, 5 times 1 is 5. Row times column, -1 times 1 is -1, 7 times 0 is 0. And then row times column, -1 times 0 is 0, 7 times 1 is 7. And you get the original matrix back. And so we'll talk more about the identity matrix later, but for today, that's it.